What makes a solution?
Alright, so here we got this red energy food dye, which will be our solute in this experiment. And the water here is going to be our solvent. The solvent tends to be more than what the solute is. So when we combine these two, there we go. The red goes into the water and makes a solution.
What types of solutions are there? Solutions can be classified by how their particles dissolve and float around, or by how much of the particles are actually dissolved. As we are mixing, you can see that all of the salt particles are dissolved in the water. This means that the solution is unsaturated and that more could be dissolved. Somewhere in between the salt we just added and the initial amount, there was a perfect spot where there was enough salt that could be perfectly dissolved in the solution. This is a saturated solution. Now we are showing a supersaturated solution because all of the salt particles were not completely dissolved in the water. As you can see, it's supersaturated because there are particles left over floating around in the water.
In this example, we got mayonnaise and water, and when these two combine, it makes a colloid. And a colloid is when the small particles of the solute combine into the solvent and they evenly disperse throughout. So as we add this mayonnaise into the water, and stir. You see the cloudiness of the colloid. And one property of a colloid is that when light is shined through it, it actually disperses the light because it bounces off the small particles of the solute. So as we see here, we see that the colloid actually illuminates. In this example, we have red pepper and water, and when these are combined, it makes a heterogeneous solution, and this is because the particles that are dissolved within the solvent don't dissolve completely. Now, as I add this red pepper in, we can see, even as we mix it, they're still sitting at the top of the water. They don't dissolve. Now, this solution can also be known as a suspension because the particles don't actually mix in with each other. In this example, we got salt and water, and when these two are mixed, it creates a homogeneous solution. And this is where the solvent completely dissolves the particles of the solute, and they're evenly mixed within the solution. So as I add the salt within the water and mix, we can see that the salt particles are starting to disappear within the water.
Affects the formation of a solution.
Okay, so these are some of the properties of solutions, and all of these things affect the forming of solutions. So number one is the particle size of the solute. Different sizes of the solute can affect how quickly something is dissolved. For example, some sugar, the smaller particles will dissolve quicker than a cube because they have more surface area. Next is the temperature, specifically of the solvent. The higher temperature will make things dissolve quicker because particles are moving faster versus a lower temperature, which will make things move a little slower. And third is movement in the glass or whatever the solution is in. If you are stirring a solution, it will make the particles move quicker, similar to a higher temperature. So if the particles are moving quicker, it will dissolve faster.
What about colligative properties?
Okay, these are colligative properties, and colligative properties depend only on the number of solute particles, not the identity, so the specific element does not matter in any of these things. So the first one is vapor pressure lowering, then freezing point depression, boiling point elevation, and osmotic pressure. And all of these things are based on the molality equation. So that is just a concentration equation. It's not based on any specific elements. And for example, freezing point depression, that's the reason why we put salt on roads in the winter, because it makes the freezing point lower, so ice won't form as easily.
What's molality and what's molarity?
Molality is similar to molarity in that both are measures of concentration, but the equations are a little different. Here it's represented with a lowercase m, and the equation is moles of solute, which is the same as molarity, but it's over kilograms of solvent, which is a little different. And over here you can see with these two glasses of 500 milliliters of water, so they have the same amount of solvent, but they have different moles of solute. So you can tell here that they have different molalities, which means they have different concentrations. And because this only has 3 moles over the same amount of solvent in each case, this one has a molality of 6, and this one has a molality of 12. So this one is obviously more concentrated. And here you don't need to know the exact element that is put into the solvent. So that's how molality relates to colligative property.
Molarity is a measure of concentration that is represented by a capital M. In order to solve for molarity, you take the moles of solute over the liters of solution. And be careful when solving for a molarity problem, because many students often confuse this formula with the molality formula, which has kilograms of the solvent on the bottom. So double check and make sure that you always have liters of solution on the bottom. So an example of a molarity problem could be a solution has a volume of 250 milliliters and contains 0.7 moles of NaCl. What is its molarity? So first of all, remember we're using the liters of solution, not milliliters. So you're going to take this 250 milliliters. You're going to take 250 milliliters and convert that to 0.25 liters. And so we got lucky. It has the amount of moles of the solute already stated in the problem. So all you have to do is 0.70 moles of sodium chloride over 250 liters. And then that will bring you to, once you divide it all out, 2.8 M, and make sure you have a capital M. Boiling point is a colligative property, and as boiling point increases, the I value will also increase, because so what solvents are trying to do is they're trying to evaporate, and ions will get in the way of this evaporation. So as more ions are put into the solution, it makes it hard for the solvent to evaporate, so it has to increase in temperature in order to be able to evaporate. So that's why as the I value increases, boiling point will increase. And this is also shown if you're solving for the boiling point using this equation. Obviously, if there's 2 ions instead of 3, then the boiling point will be lower because it'll be multiplied by a lower number. So that's why as more ions are put into the solution, the boiling point will. Ionic substances are good conductors in water because water is a polar substance and ionic substances are also polar. And according to the like dissolves like expression, polar solvents will dissolve polar solutes, and ionic substances are also electrolytes. So when they are in aqueous solutions, they are able to conduct electricity